remind you that we're going to have a couple of quiet hours after this. And then there is a dinner at Avalon Park. There are buses leaving from here at 7, meeting in the parking lot up front. Please start gathering around 6:45 if you want the bus. If you're driving, there are driving directions here, and make sure that Kim is going to email another copy of that. So check your email in the next couple of minutes. You should get a reminder of the driving directions. I can read them if people want. I think that's overkill.
Parking is limited.
Parking is limited, so it'll be a good idea if people can carpool. Maybe people raise their hand if they're planning to drive there, and then other people can talk to them. So look around, find a victim. All right. So it's a great pleasure for the last talk of the day to introduce Dan Fries. We'll talk about Orientifold worldsheet anomalies.
Thank you. So I'm going to discuss the following theorem, which is that the worldsheet theory of the type 2 superstring with Orientifold is anomaly free. Well, as it stands, that's not a mathematical statement, but there will be mathematical statements out of that. And this is part of a larger joint project with Jacques Dissler and Greg Moore, in which we investigate various topological questions around the type 2 Orientifold. And in particular, one of the important pieces, and certainly an important piece in proving this theorem, is the geometric nature of the Orientifold fields. So we'll discuss that. So anomaly problems in string theory have a long history. And there was a very vigorous period in the mid-'80s. I'm certainly not going to review all of it. But I think it was around 1983 that Alvarez, Gomez, and Witten showed that the type 2 supergravity theory, which is a kind of low-energy field theory approximation on 10-dimensional space-time, that had no local anomalies. And then the big advance was in 1984 with Green and Schwartz, who showed a similar thing for the type 1 superstring for its low-energy supergravity with some string corrections. They did their anomaly cancellation, and that was really the start of the big superstring revolution at that time. As far as the worldsheet theory, shortly after that, Witten gave an argument, and then I generalized it for showing anomaly cancellation for the worldsheet theory of the heterotic string. And the same arguments work for the type 2 superstring. We actually wrote them together in a paper later on. And but as far as worldsheet anomalies, that was it. And the type 1 superstring was certainly around since the early days of string theory, long before the mid-'80s. And that problem wasn't addressed. The Orientifold construction, of which the type 1 superstring is a special case, the Orientifold construction, I think, was in the late 1980s. And so, in a sense, this kind of fundamental consistency check has been around for a long time as an open problem. So I'm devoting the lecture to it. Well, I think if you're interested in string theory, then it might have been more interesting news if I came and told you that there was an inconsistency. Sadly, or happily, I can't do that. But it turns out that the story about this anomaly cancellation is a little bit subtle, at least it was for me. And So that's one reason I want to tell you about it. It's part of, as I say, a bigger picture, which doesn't really kill string theory, but rather, I think, presents some kind of beautiful evidence. These topological phenomena, which you can see at various scales, and which cut across various scales and various descriptions of a theory, are something you can really test. And here, the kind of topology that enters into this anomaly cancellation plays a role in other parts of the Orientifold theory that I won't discuss today. There are also mathematical reasons. And some of the mathematics that goes into this, well, there are ideas from geometric index theory. And those ideas, a lot of developments actually came in the mid-'80s out of the study of anomalies, in particular Witten's global anomaly formula. And we'll use some of those ideas, but we'll also use more recent ideas, which, for example, ideas in differential cohomology. And although I won't discuss it much, ideas in topological field theory. All right. So let me begin by telling you what an anomaly is. So let's imagine that we have an n-dimensional quantum field theory, and you should imagine in some Euclidean version. And for the worldsheet theory that we're going to study, n is equal to 2. So let's suppose that sigma is a smooth n-manifold. Then part of describing this theory in a Lagrangian context is to tell what the fields are on sigma. So we'll have some space of fields. Now, these fields, I'm not going to give a mathematical definition, although we could, but the fields, there are lots of different types. There are often scalar fields, which are just functions on sigma. We might have connections, metrics, and so on. We might also have kind of discrete fields, like an orientation on sigma, or a spin structure, or perhaps a finite cover, something like that. And we can also have spinor fields. So these fields are bosonic, and in general, all fields kind of fiber over the bosonic fields. So in the path integral approach, one can integrate out over the fibers of this, the fermionic fields, and that integral produces an effective action, which is a function from the space of bosonic fields to the complex numbers. So this is an exponentiated version. So you might think of it as e to the I as effective, although this exponentiated version indeed could be 0. But what happens is that often, so this is the nice situation, and then what you would like to say is that you integrate this over the space of bosonic fields, and of course that's where all the analytic difficulties of quantum field theory begin. But you may already have a kind of formal difficulty at this stage. Which is that the effective action might not naturally, the exponentiated effective action might not naturally be a complex function, but rather a section of a complex line bundle. So we might have a complex line bundle over the space of bosonic fields. So this is actually a Hermitian line bundle with a covariant derivative. And we might have that the effective action, that's exponentiated effective action, is a section of that. And now even if we have a good measure here, there's no way to integrate a function. We're trying to sum a function with values in a vector space, a complex line, and the line varies. We need values in a fixed line to be able to do that. Yes?
going even a step further back, how do you know you can integrate out the fermionic fields?
Well, I'll tell you in the problem that I'll do, let's say. So that's done by some kind of construction with Dirac operators, by taking a Pfaffian of Dirac operators, typically. So that's what I'll do in this problem. Okay. So, so what you need in order to overcome this is you need a trivialization, which is a basis of each of these. And you want it to be compatible with the metric in connection. So in other words, the norm of this function is identically 1, and it's compatible with the covariant derivative in that it's a flat section. So you'd like to have that. And so the anomaly, well, in the first instance, it's the obstruction to the existence of that global basis. So that's what the anomaly is. And of course, it's easy to say what that is. It's just the holonomy of that line bundle. If all the holonomies are 0, then such a section exists. But you see, if we have such a section, then we'll simply look at the quotient, which is now a function. And then, at least formally, we are able to integrate that. Of course, we have the problems with the measure and so on. But we need to specify this in order to specify the quantum field theory. So one level of this problem is just the obstruction. But the second level is to specify this trivializing section. So this has echoes in some of the talks we heard Monday from Simon Donaldson, Dominique Joyce, about orientation questions in defining, say, Donaldson-Thomas invariants, where you need orientations to get the number. There's a question about the existence of such orientations, and then a question about actually finding canonical orientations. So the same thing here in this anomaly problem. So that's a discussion that I could have given and indeed did give in the mid-'80s about what the anomaly is. There's another aspect to this that was also discussed in the mid-'80s, which is a kind of Hamiltonian version. So in the Hamiltonian version, we would study an n-1 manifold and think of the theory on that manifold cross time, and you want to produce a vector space. And so, again, you might, so to speak, partially quantize. And for all the bosonic fields on Y, you would try to produce a bundle of vector spaces, a bundle of Hilbert spaces. But quantization typically doesn't produce a vector space. It typically produces a projective space. And the problem with a bundle of projective spaces, if you want to go further and, so to speak, quantize in this direction, is you want to do something like take sections. And then to do that, you want to lift the bundle of projective spaces to a bundle of vector spaces, Hilbert spaces. So there's, again, an anomaly, we might call alpha of Y, which is, so to speak, the projectivities. The kind of obstruction to lifting to a vector bundle. So that's also, in a sense, one-dimensional in the same way that a line is a one-dimensional vector space, what we see over here. Everyone got this? So a more modern point of view on this anomaly, it emanates from the understanding that the anomaly itself should obey locality, the same way that the effective action is a local function of the space. And so these should fit together into, well, so we should fit together into alpha. We might think of it as some Bordism theory of manifolds. We have to include n-1 and n manifolds, and together with these fields. And, well, we'll go somewhere. I'll just use some symbol. And this is going to be actually what I would call an invertible quantum field theory, an invertible field theory. So invertible means that, so first of all, we'll be able to extend this actually to an n+1 dimensional theory, to have n+1 dimensional manifolds. Because, for example, here we have n manifolds, we have this line bundle. If we take a loop in this space, then that loop combined with the sigma is going to give us essentially an n+1 manifold, and we'll get a number out in R mod z, which will be the holonomy. So we're going to get something that gives in the top dimension some numbers in R mod z. In dimension n, it'll give lines, and in dimension n-1, these, gerbs. And those are invertible in the sense that the numbers, if I think of them as exponentiating as complex numbers, those numbers are non-zero. The lines, when I think of vector spaces under tensor product, a line has an inverse line, and so on. So the anomaly itself is a field theory, but of a rather special type. It's an invertible field theory. And so, so what we need to do, this thing we need to do, we need a trivialization. So this data that we need is a trivialization of this anomaly theory, but we truncate and we only think about the theory on n manifolds and below. We don't think about n+1 because we're only trying to make this n-dimensional field theory. So that's a more modern point of view. And in today's story, this alpha is actually the tensor product, the product of two different theories. So one of these theories comes from the fermions, and it has to do with Dirac operators. And that's very much part of this geometric index story that dates from the mid-'80s, although there's a kind of twist there that makes it more difficult. And this alpha 2 is a kind of bosonic surprise. And it's not certainly by any stretch the first time that there are bosons that contribute anomalies. The self-dual field, going back to the type 2b superstring with no Orientifold, certainly contributes an anomaly. And the Green-Schwarz effect is about a certain kind of bosonic anomaly. But the one that occurs here is not something I've seen elsewhere. OK, so that's the kind of background picture of what an anomaly is. And the theorem certainly is proved at the level of showing that there exists such a one. And one nice feature in our story is that alpha 1 and alpha 2 are both, in fact, topological theories. So in general, when you have quantum field theory, it's not topological, despite what some of us may think. And even this anomaly theory is certainly not topological in general, but it happens in this problem that each of these pieces is topological. And that's a good thing, because topological field theories, first of all, have their own methods to study, and if they're invertible, even better. And even better if we can extend the theory down to lower dimensional manifolds. And if we can do that, then we can study this with homotopy theory, because saying it's invertible means that we can sort of invert everything in the Bordism category, and what you get is something that belongs to homotopy theory. It's called a Madsen-Tillman spectrum. And the target is, again, a spectrum, and you can study a theory as just a map in the world of homotopy theory between those spectra. And so constructing this isomorphism is then a matter of constructing a homotopy between those maps. And there's still a few details to straighten out there, but I think that's going to be a way to address this problem at the finer level of specifying that map. All right, so let me tell you about the fields. And so there are going to be fields on the worldsheet, and then fields on the space-time. So the worldsheet itself is sigma, which is a smooth, closed, two-manifold. And the space-time, I'll call X, is actually a 10-dimensional orbifold. So here I mean orbifold in the sense of differential geometry, orbifold in the sense of Satake, Thurston, and so on. Some of you might know it as a smooth version of a Deligne-Mumford stack. Okay, and so in each case, so here are the fields. So in each case, we're going to have a Riemannian metric. And the basic field is, of course, the string, which is a map from sigma into X. Now, what does it mean to say that we have an Orientifold? Well, I want to interpret that as saying that we have an unramified double cover called the Orientifold double cover. So it's usually said by saying that this is space-time and it has an involution, but I'll think of the quotient of space-time, and that is giving the data, this Orientifold double cover. And in the special case of type 1, then this X is simply XW cross sort of point mod a cyclic group of order 2, which we'll just call BZ2. So in other words, this is usually taken to be smooth. We just have a smooth manifold with a trivial involution. So that's the special case of type 1. Okay. Well, now there's another important field, which is that if I take the pullback of this double cover, then I need an isomorphism with what I might call W1 of sigma. So that's represented by a double cover, which is the orientation double cover. So any manifold has a canonical, smooth manifold has a canonical double cover, where a point of the double cover is an orientation on the tangent space below. And saying that we have this map nu is saying that we really have a lift of this map phi to the double cover. So that's a condition on what a map in the Orientifold should be. It's part of the Orientifold construction. And now we have spin structure on the worldsheet. And in the type 2 theory, there are actually two spin structures. And locally, on any patch, you have the two spin structures which refine opposite orientation. So a spin structure has an orientation as well. And we should have two spin structures, one for each underlying orientation. But globally, those don't necessarily fit together to a spin structure. For example, if sigma is not orientable. So the challenge in this Orientifold is that the Riemann surface sigma might not be orientable. Indeed, that's the interest there. So instead, those two spin structures patch together to a spin structure on this surface, which is the orientation double cover. Now, the orientation double cover is canonically oriented, just by its definition, and this spin structure should be compatible with that orientation. So that's the data of the spin structure. And then there are the fermions, or the fermionic fields. So I'll just say what they are, but we won't. So psi is a kind of plus spinor field on this cover with coefficients in the pullback of the tangent bundle. And then there's another one, which is a minus spinor field, and it has coefficients in the cotangent bundle. So that's a complete catalog of the fields in the worldsheet theory, and we'll need all of them to talk about this anomaly problem. Now, on the space-time, there are lots more fields, and there are only two that we need to talk about the anomaly problem. The first one is called the B field, and the second one is a kind of spin structure, but it's a twisted version of a spin structure. So I'm going to explain those a little bit later. All right.
Of X.
Say again?
Should it be the tangent bundle of X? Or is it...
This one's the first one, psi, has to do with the tangent bundle of X. So I'll just pull back to here. And the second one is purely intrinsic to sigma. So it's to do with that. That's sometimes called the Rarita-Schwinger field. Has to do with the supergravity theory on the worldsheet. Okay. Well, I don't need them for today's discussion. So there are certainly Ramon-Ramon fields, there are fermionic fields, and so on the space-time, but they won't enter into the discussion. But those two will.
Self-dual field.
Pardon me?
Even the self-dual field.
The Ramon-Ramon field. Yeah, that doesn't enter into the worldsheet anomaly. No. Okay. Other questions? All right. So to kind of get rid of all that and to summarize, we'll have sigma, which is our surface, and the fields on it are Riemannian metric. We'll have a vector bundle, which is rank 10, real vector bundle with a metric and connection. So that's the pullback from the tangent bundle. We'll have this spin structure on this orientation double cover. And then we'll have a B field and this spin structure, twisted spin structure, which is on the vector bundle. So we can study everything just in terms of data on the worldsheet. All right. So now let me come to Ron's question. How do we integrate out the Fermi? So I didn't write down these spinor fields because we're going to integrate them out. So in other words, this collection of data is what I called in the general story F prime of sigma, the bosonic fields. All right. So now how do we integrate this out? This is the story of the Pfaffian. Well, we want to consider a family, smooth family of these world sheets. So we can do this in a family. So we have a family of that data. And when we integrate out the fermions, what we study is the Dirac operator applied to these fields, to this plus spinor fields with coefficients here, and this minus spinor field with coefficients here. And since we're in 2 dimensions, the Dirac operator has the special property that there's a Pfaffian line bundle. And that's the thing I called alpha over there, alpha 1, for that family over S. So this is a Hermitian line bundle with connection. And the first result is to say that this is flat. There's no curvature of this. And that follows because, you see, all the curvature comes, a formula for the curvature comes from the differential geometric information, from the metric on sigma, from the metric and connection on these bundles that you're coupling to. And those all exist on sigma, which means that those curvatures are pulled back, and the polynomials you make from the curvatures are pulled back to sigma hat. And you have to do an integral over sigma hat, but because you're integrating over this orientation double cover and the 2 sheets are oppositely oriented, that integral cancels. And so right away, you're put into a topological situation where this thing is flat. So this problem then involves just the holonomies. There's no curvature. So now if we want to study the holonomies, well, in that case, we just want to study a circle in here. And so over that circle, we'll have a 3-manifold N. So that's like the 3-manifold there. And so the theorem is that the holonomy, it's really minus the holonomy, around that loop, I'll just call H. And that's given by a certain invariant in index theory. It's roughly the Atiyah-Patodi-Singer 8 invariant. But there's an extra factor of 1/2 because of the Pfaffian. And, well, it's coupled to this bundle. So this pi star of V minus the cotangent bundle of n hat, but the relative cotangent bundle. So we have two different Dirac operators, one's plus, one's minus, and by the time you factor that all in, you get this difference of these invariants. So that's one of the theorems I proved with Bismuth, but that's a version of Witten's global anomaly formula, as I said, from the mid-'80s that allows you to compute that. Now, in this situation, we know that that's a topological formula. We know that if we move the data, because of this flatness, that it's topological. And the game is to take that formula and push it down to a formula on sigma. But that's not quite so immediate to do, and there are several steps to do that. So one of the first steps is, because it's topological, and this n hat is spin because of the alpha, then we can essentially replace it by a trivial bundle of rank 2. And so we get a formula something like that. Well, all right, so I want to tell you the kind of formula that we get by pushing it down on n. So I need to express that formula in a topological language, and so let me introduce some of the kind of topology that's involved. So there are three things here. So the first thing that's involved is a certain cohomology theory. So I'm going to let KO be what's called connective K-theory, connective real K-theory. So in other words, KO naught of some space is just the real vector bundles stabilized and made into a group by direct sum. We're more familiar usually with the periodic version, but this is actually the more primitive one. And this is a ring because we have not only direct sum, but we also have tensor product. And I'm going to define R to be a kind of truncation of this KO, where I'm only going to remember a little bit of KO. So the way to tell you that is to tell you what the homotopy groups are. So here's K, and here's pi K of R. Let's say Q, pi Q of R. So the homotopy groups, well, in dimensions less than 0, they vanish. That's already true for KO. And then the ones from 0 to 4 are the same as the ones from KO. So that's Z mod 2, Z mod 2, 0, Z. And then above that, that's the truncation. We make it 0. So we're truncating this KO. That will enter a few different ways in this story, this R cohomology. One way it's entering here is that we want to consider this Pfaffian bundle. So in index theory, there's a whole index for this thing, which lives in the KO theory. That would be computed here. We only want that Pfaffian lowest piece, and so it's computed by this truncation. But that truncation is also going to come in with the B field, which is one of the things that matches various pieces of this story. All right, so that's the first piece of topology. Second piece is what I might call tome twistings. So it's a general construction. If I have a real vector bundle, then, well, out of it, if you picture the real vector bundle this way over space Z, then what we can do is sort of collapse infinity. And if we collapse that into a single point, we make what's called the tome space of this vector bundle. And so we can define the R cohomology twisted, it turns out, by minus E of the vector bundle, is by definition the R cohomology of this tome space. But we use reduced because we have a natural base point from the stuff that we collapsed. So this cohomology looks locally on Z as if we're doing ordinary cohomology in whatever theory we're doing, in this case R. But we need to know this twisting. Well, if we have a spin structure, then what the spin structure gives us, if it's a spin structure on this vector bundle, what it gives us is a class. Oh, sorry. Yeah, so that's one piece. Now, if Z is compact, then we have a topologist version of integration, which is going to go from the R cohomology of Z to the R cohomology of a point. And if I want to land in degree Q, then where I should start is in degree TZ plus Q. So this is a natural integration that we always have on a compact manifold. And you should think of twisting by this tangent bundle as the analog in de Rham theory of, you see, on a closed manifold, we can't integrate differential forms, but we can integrate densities. So densities are a twisted version of differential forms. And in the same way, this twisting by the tangent bundle is like densities for any cohomology theory. So we always have an integration like that. And the one that we're going to need to push down this formula is if we have an orientation. So in this case, that's a spin structure. Then this gives a class in this twisted cohomology. And so now we can now integrate ordinary classes by just multiplying by this class, using the fact that R has this ring structure. So again, in de Rham theory, once you have an orientation, you can convert between differential forms and densities. And that's what that class does for you. All right. So there's a final thing that I need, and I don't really have time to explain, which is our differential cohomology. So very briefly, I'll just explain it by explaining a differential version of H2 of a space with integer coefficients. So H2 of a space with integer coefficients is the space of line bundles over Z. These are complex line bundles up to isomorphism. So this is a discrete abelian group. The differential version of that is line bundles which are Hermitian with a covariant derivative, and that up to isomorphism. And obviously, if you have the differential geometric data, you can forget it, and you can just map there. So if you think about the structure of these things, then these actually form a Lie group. They form an abelian Lie group. And they have a natural map, which is the curvature, which maps us to two forms, which are actually closed. So something in here has a topological significance, which is just telling you the component we're in this Lie group, and it also has local information given by the curvature. So we're going to use that as a little bit of a crutch in the index theory. I'm not going to explain the details, but to push that formula down. And that is one of the modern tools which helps with this problem. that goes beyond the technique certainly available in the 80s. This is one of the modern tools in index theory. But we're also going to use it in a minute when I explain about this B field. All right. So let me now get back to the problem. And so I said that we have this holonomy formula like this. And what we're going to do is rewrite the holonomy formula. And I'm just going to tell you really the final answer. So it's going to be an integral over n in the sense of this kind of integral. And what we're going to integrate is a class I'm going to call delta times we're going to integrate just the vector bundle minus the trivial bundle of rank 2. Now I have to tell you where all of these things live. Well, this delta is what I get by pushing forward over the double cover this class X alpha. So I said the spin structure gives us this class, and in our problem that lives on this double cover of the in this case, the 3 manifold, and so we can just push it down over the double cover. And yeah, okay. So this is a class which, if we do it purely in cohomology, then we would get a class in some R cohomology twisted by the tangent bundle. But we can actually do it in this differential theory, and what we find is we get a flat class. So it amounts to saying it lives in precisely this place, where this tau is this Thom twisting, but reduced, so the degree shift is out of there. And this V minus R2 is that vector bundle. And I told you that real vector bundles give you a class in KO0. And KO0 has this quotient, this truncation, which is R0. And now if you multiply that out, then you get a class in R of degree tau minus 1. You integrate over a 3 manifold, you get down to R of a point in degree minus 4. And if you look at this chart, in degree minus 4, if you put in R mod z coefficients, you actually get a number. So that's the kind of formula that one gets. And let me just, since I'm running low on time, what time did I start? Or how much time do I have left? 10 minutes or so? 15 minutes. No, better, 15. No, you can't reverse negotiate. 15. All right. What? All right. So, okay. So let's rewrite that formula just once then. So remember that if we have this family that we wanted this Pfaffian bundle, so that was alpha 1 of sigma, and we can write that in a similar way by integrating over the fibers of this, integrating this same kind of expression. Now, I said that we could subtract off something of order 2, but in fact, there's a little lemma here, which tells that 8 times that class is 0. That 8 has a meaning in the string theory and fermions and so on, especially in the heterotic string. But here, we'll just take it as a purely topological lemma, and it's something you prove by calculating something universal. Okay, so that means that we can substitute here a 10, which is good because that's then V had rank 10, so that's the kind of reduced bundle. All right, so you get this kind of Baroque-looking formula. And on its own, that formula doesn't give 0 by the things I've told you. So there is an anomaly. And if that's all we knew about the string, and we didn't take into account these things, then we would be stuck. But in fact, what's going to happen, as I told you at the beginning, is that there's also an anomaly from this B field. And so let me now say a word about this B field. So the B field is an abelian gauge field. It's much like the Maxwell field in electromagnetism. The Maxwell field has a local, in classical electromagnetism, it's given by a two-form. One of Maxwell's equations says that that two-form is closed. And similarly here, locally, this is given by a three-form. Well, this was originally on X, on the space-time, and it obeys the kind of Maxwell equation that says it's closed. Now, that's good enough to do a kind of classical theory of the B field. And what we want to do is put a term into this effective action, this A that we talked about somewhere at the beginning. And that term should be integrating the B field over this worldsheet. So we should pull back the B field and integrate over sigma. While the B field is a three-form, sigma is a two-manifold, so of course that doesn't quite make sense. But in a family of such surfaces like this, if we pull it back, then we can integrate and get a one form on the base, and that one form should be the differential of some function. So that's the function that we want to get at. Now, in the Orientifold, it's not quite true that H is a three-form, but rather it's twisted. And it's twisted exactly by the Orientifold double cover. So concretely, it's a three-form up here on the Orientifold, and under the deck transformation of this double cover, it changes sign. So it's like a density. So when I map in, I would need to have it integrate something like a density. And that works kind of nicely because of this field nu, this isomorphism, that says when I pull it back, I get a three-form up here, which is odd under the involution. So in other words, in a family of surfaces, it is behaving something like a density. So there is no problem in integrating this H. That doesn't present a problem. But these abelian gauge fields obey something called Dirac charge quantization. And that's where one of the ways in which this differential cohomology enters the story. So not as it did here as a kind of formal tool in index theory, but now as something geometric, really, in the physics, which is that if you have this H is like a flux, so it's living here, but the flux is quantized. And quantizing it says that when we integrate around cycles, we should get integers. But even better, we should refine those integers to live in some abelian group. And so we need to pick some kind of cohomology theory that refines those. And the combination of these is exactly something that differential cohomology does. So the upshot is that, that one of these gauge fields lives in a cohomology theory, and the B field represents a class in exactly this R cohomology, twisted again by W, but in degree -1 of X, well, or sigma, whatever. So if we look at this R cohomology, if we're in degree -1, then we're going to lose this bottom Z. And so what we have is Z2, Z2, 0, Z. Now the Z that's up here in degree, it will be in degree 3 when I shift. That Z, when I tensor with the reals to see what kind of differential forms I get, that's the 3 form. And so we indeed get the 3 form, but we have these extra Z mod 2s. And now you should ask why, in the superstring, why did I pick that particular cohomology theory? And that's a little bit of a story involving other parts of the theory. But if we do the type 2 case without the Orientifold, so I should have said right at the beginning that without the Orientifold, we have one more piece of data, which is simply a section of this Orientifold bundle. In other words, we just have the trivial bundle there. If we do that, then this is just a class in R-1. When we pull it back to the world sheet, we get a class there. And now this R theory, being built out of KO, in order to orient it, to integrate without any twist, we need a spin structure. And in the oriented superstring, you exactly have a spin structure, you see, because you have one on the double cover. But saying that you have a section here, that pulls back to a section here, which gives you exactly an orientation on sigma. So in the type 2 string, you have oriented strings. That's where it comes from this point of view. And therefore, you can integrate using that spin structure, the left or the right spin structure. And so when you do that, those E2s give you some subtle signs. And so, for example, that encodes exactly the signs that distinguish type 2A from 2B. And there are other constructions in string theory that kind of justify putting in those things. Well, so in this story, with the Orientifold, we get this extra twist. And now, I really am running out of time. So this is where, oh. So it was really kind of a puzzle. How to define, say, the integral over sigma, or that push forward, of this B field. Because in this twisted case, the twistings don't quite line up. You have this W twisting, which is a W1 twisting, this kind of density twisting. That was good for defining the differential form integral, but you need a spin structure to integrate in this R theory, and that spin structure is only up here. So that kind of stymied us for a long, long time. And the resolution is that this is, in fact, anomalous. And I don't have any really good way to tell you that, certainly not in 2 minutes. But it turns out that there's some kind of universal classes in this R cohomology. You have to do it equivariantly. So you see we have this Orientifold double cover, and it has a classifying map to this space. And over here, there's some universal class that we can use to pull back and use to integrate. And that universal class, when I pull it back here, it's again a kind of differential class. When I pull it back here, it becomes trivial. And we need to give not only that class and a kind of differential version of it, but also a trivialization when I lift. And then what you do is you use that trivialization, exactly gives you the right information to define this thing. But it's no longer a number, which would be the usual B field amplitude, but it's rather a section of a bundle. And the bundle has a formula, which is something like that. But it's some universal kind of class pulled back. Say Q was that classifying map of the double cover, and then we multiply by the B field. But it's a topological formula, so it doesn't see anymore the usual 3-form H that comes out of the differential theory, but it only sees the cohomology class, the kind of component of this B field. And so this anomaly is, again, topological. And, well, again, I don't know quite how to justify that that's the right thing to do, except that it works, and in the case when it's oriented, it reproduces the other answer. And so you see that to cancel the anomaly, then, is a matter of, well, we'd like to cancel these things after integrating. And, well, if these things were the same, then that would cancel it. It turns out these things aren't quite the same. But there's another cohomology theory that this one maps to. And when I map over there, they are the same. And not only are they the same, but there's an isomorphism between them. And that's a rather abstract topological way of describing this last piece of structure, which is this twisted spin structure. So there's something built out of this B field, which gets isomorphic to this thing. Trivializing this, back to the Thom twistings, that was what a spin structure does. And so this is a kind of twisted version where we don't make this isomorphic to 0, but isomorphic to that. And so the anomaly does cancel, and the map that's going to give you that section that would enable you to define the path integral, and indeed the whole theory, is given by that twisted spin structure on space-time. So that's a rather Baroque story, I'm afraid, for this old question. And it's a rather abstract topological story because the anomaly on the worldsheet has to do with these mod 8 kind of things. But just to finish, when we come to space-time, then the B field and this twisted spin structure that I alluded to in an abstract way have really concrete models. And just the same way that, say, a KO class has a concrete model as a real vector bundle. So the B field has a very concrete model in terms of, well, there are lots of different models, but the model that really works nicely here is to have a bundle of algebras of a special type. They're actually central simple Z2 graded complex superalgebras, and there's a way to twist them. And that concrete model is important when you go to talk about Ramon-Ramon fields, because that model can be used exactly to twist the idea of K theory and KR theory. And so in that space-time story, this B field ends up doing that. And the spin structure is also something very concrete, just as a spin structure is in differential geometry. This one is too. Spin structure is a certain reduction of the frame bundle. And in this case, you have an orthogonal frame bundle. This B field gives you some kind of double covers, and you can use that to describe very explicitly in frame bundle terms the spin structure. So I don't want to leave the impression that these are just located in abstract topology. They have sort of isomorphism classes, which are located there, which enter into the worldsheet story. But in the space-time story, they have very nice geometric manifestations. OK, thank you.
So your point 2, when you have to find a section with norm 1, is it non-trivial because your space of Broad-Infinite field is not connected, I guess?
Yes, I should have said that, right. So the question is, why is that, this business about not only proving that the anomaly is trivial, that you have a section, but actually defining the section. If the space of fields is connected, then there's just an overall phase, and then that doesn't really matter. But if there are different connected components, then the relative phases play a role. So they appear in lots of physical theories, like theta angles, discrete torsion. There are lots of ways in which they appear. And in fact, differences of trivializations, if you think of the whole topological field theory, a difference is going to be an invertible topological field theory one dimension down, which is basically a topological term in the action. So saying, fixing that isomorphism is fixing those topological terms in the action. Yeah, Simon.
Does the fact that X is 10-dimensional enter?
Well, it entered here in a mild way because, we had the V minus R2. The R2 came because of this Rarita-Schwinger coupled to the tangent bundle. And I exchanged that to V minus R10, and I told you that the spin structure has to do with that. So having this thing of rank 10 sort of plays a role because of this 8 that came in this lemma. So there's a subtle way in which at least the dimension mod 8 comes into this story. Yeah, so the mod 8 dimension did enter that story. Yeah.